Thanks everybody for coming. I know that you were incentivized because he's here and you need to be here to look good, but that's good because there's some interesting stuff we're going to talk about. And pretty much everything we're talking about, if my presentation will go forward, is why are you not advancing? There we go. Okay, it's going to have to do that. You may have noticed on the previous slide there was a US NSF logo. All I'm going to talk about in this talk is basically developed as a part of that project, which was a project specifically to look at the idea of how can we take heterogeneous data sets and in this particular instantiation, convert them into a semantic representation so that they could then be searched as a corpus. And we're not all the way finished with that. We still have a little bit left to do. But what I'm going to show you is some, not just what we planned to do, but some other things that came out of the research. Because as you can probably imagine, when you go into a grant, you typically have an idea about what you're going to do. But then as you go through doing that, you work out, oh, some of it doesn't work. And then there's other pieces that you absolutely need to create. Otherwise, it's going to be very difficult for you to actually get anything done within the project. And I can point that out. So all of this is done in the alignment with FAIR, findable, accessible, interoperable, and reusable data and everything else. As a consequence of this being a FAIR project and the timing of when I submitted the proposal back in 2018, I had to write a data management plan, right, which is what we have to write to get grant funding these days. And what I heard after the fact, after I got the grant, was that the data management plan was the best one they'd ever seen. And they started to even talk about it in workshops where they were saying how to write a data management plan. And I'm like, let me go back and read my data management plan and see what I've committed to, because hopefully I can provide it. Thankfully, I didn't overcommit myself, but I'm not completely sure about that at this point. So anyway, so we're going to talk about this thing called SciData Framework, which is all about modeling research data. And then some kind of things that we built along the way that are based off of that. And I'm hoping to show you a really quick demo at the end of something that's the more recent stuff we've worked on, which is using a technology called Shackle, which is the shapes control language. And hopefully we'll have a little bit of I'll be able to bring it up and I'll have enough time. So we all know about this. This is just me putting up a slide that says, this is the traditional model we've been in for so long that we need to get out of, which is we publish a paper and it has a section on what it was we studied. It has a section in it on how we did the research. And then it has a section that nominally reports the data from that work. But of course, these days, we now know that while it does report data from the work, it doesn't really ever report all the data from a piece of work because we can't fit that in a publication. And even if you tried to put that in supplementary information, possibly the publisher would even go, no, you can't put it in a PDF SI because it won't fit. So what we really should do these days is also put it in as SI and link it, either to Figshare or Zenodo or put it up there. This is the model that we started with in my group when I started down the path of coming up with this thing we call SciData. And so thinking about those three pieces of the puzzle of how we publish our data right now, I kind of sat back and started thinking about, well, what do I really want us to be doing? Because, okay, we're not doing the right thing right now, but what should we be doing? So this is completely utopian. We want unambiguous identification of species, samples, instruments, and whatever else you want to add on so that we can reference to them. We want to have complete and accurate description of the scientific workflow that we go through. And so, yes, one of the things I'm interested in is not just about capturing the data, but also capturing the process of doing the research. And of course, that means nominally something like an electronic lab notebook. And we'll talk a little bit about that coming up. Collection, annotation, analysis, and archiving of all experimental data. Again, yes, this really is utopian, right? This doesn't happen right now. Maybe it does in certain specific situations, but not generally at all. And in order to be able to do that, of course, what we really need is all information born digital. And when I talk about this, I didn't invent kind of like this way of talking about this. It was actually this man that invented it, because at least for IUPAC, he said we need a digital IUPAC. And that means, to me, it means digital chemistry, or chemistry born digital first. So the big thing about all of this is, if we even started talking about this, everybody would roll their eyes, because not only do we have to convince the research scientists to kind of like think first about making stuff digital, but also that would enable them, it would require them to put in a lot of metadata information that they really, really, really don't want to do, right? It takes up time. It's just another form that they have to fill out, and we're over filling out forms. So in a sense, we have to try and build something that can maybe do some of that stuff for us in the background. And so we actually want to have maybe a system that will annotate who's doing that work in the background as we enter the information in, store it permanently, so it's permanently open and reusable as appropriate, of course, from a IP perspective, and preferably immutable. And of course, what I mean by immutable there is that it cannot be changed once it's been created, so that there's some way to nominally trust the information that's present. And I'll show you an example of that coming up here. So what is this thing called the SciData Framework? Well, basically taking a paper that I wrote, in 2016, which was basically analysis of what we do in terms of publishing data in research literature, that we need to have some framework of how we capture not just the experimental data from research, but also the metadata that describes the context of that experimental data. Because what we know is we can have data, but if we don't have a lot of descriptive metadata about it, we really can't put it in context, and we can't link it together correctly. We need to, for instance, if you're doing solubility measurements, you need to have, if it's a solid solubility in a liquid, you need to have a temperature at which that occurs. Otherwise, the solubility value in a concentration sense doesn't really make any sense. You can't think about it properly. So the pieces of this puzzle are the methodology, the system, the data set, which I had on the first slide or the second slide. Oh, no, it's back. Okay, gremlins. And we also need some other information in there. The finding aid. So this is metadata about the overall packet of information. So whereas methodology and system metadata, kind of a metadata for the data set, the finding aid is kind of like pulling out the most important metadata from the whole thing, so that we have a way to find this information, assuming there is a huge corpus of information that can be found. And then, of course, we need to have unique identifiers to be able to deal with that too. I implemented this idea in some examples in Excel, in a MySQL relational database, and XML, and I ended up coming to the idea that JSON-LD, which is a representation of RDF, the Resource Description Framework, or triples in a triple store, was really the place to go. And in order to do that, I needed an ontology to describe these components. And so the idea from the JSON-LD perspective is a relational database has a very rigid schema. So different types of data really don't fit into the same schema. So that's really not that good. However, semantic data, which is represented in what's called a graph database, is literally schema-less. It has whatever modeling is necessary to capture the data and its relationship to the metadata, and that can be different, obviously, from different data set to data set. So, in a sense, we needed something in the middle. It was in a graph database, but having some way in which there's some kind of structure in the graph sense to be able to search against the data that's been put in the graph, so that we can actually look across different data sets that have been put into the graph and do something with the data. And that's how we came to the SciData ontology that goes with the framework. Some of you may know about semantic data, some may not. So here's a quick primer on that. RDF, Resource Description Framework, is the idea that any knowledge can be represented using a triple, which is the identification of a subject, and then a predicate that then relates that subject to an object. The object can be another subject, as it were, or it can be a literal value. So it can be a string, it can be a number, a Boolean, whatever. So that's the traditional triple, but in the current instantiation of JSON-LD, there's also the capability of, okay, and it just is, I'm not touching the computer, I guess it's the problem. There is the possibility of, in the JSON-LD document, putting it in an @graph section. And what that simply does is it gives a name to the data that's in that particular document, which then gets converted into these triples in the triple store. So you have a quad when you talk about a subject, predicate, object, and then the graph name. This is particularly useful for what we're trying to do because we're trying to represent data semantically. And then when we look at it in a semantic sense and we do a search on it, it may well be that we haven't quite got the right organization of the data. And therefore, we need to think about how do we put a new version of it into the graph database. And having a name on each of the triples is a great way to be able to delete out all the triples that are about one set of data in one single JSON-LD file, and then be able to put the new version lock stock into the graph to replace it. So it's a very practical way to move forward with it. Okay, so what does the structure look like? So the basis of this is that anything in a JSON-LD document that has an @ symbol at the start of the name is a specific keyword defined by the JSON-LD specification. So @context, @base, @graph, and so on. Those are defined by the JSON-LD specification. Now, outside of that, we can nominally put anything we like in this document. And the way what we've chosen to do is not basically require anything. If you know anything about JSON, you may know that there's something out there called JSON schema, which is kind of like the equivalent for the XML schema idea that exists. And XML is very good for, this is really great, it's really good for having data in an XML file that is standardized and can be validated. In this context, we've not done anything to do with, that's the problem, okay. He solves all the technology problems as well, right? So what we've done is basically said, okay, there's going to be these different sections of this document, and none of these are required, but in a general sense, you can obviously imagine there are certain fields that should really be in there, otherwise it doesn't mean much. So this stuff at the top is, like I said, the general metadata, and we're thinking about it as a finding aid. And again, the idea is that at some point, we hope there's going to be some infrastructure out there where there's a lot of research data available. And the biggest problem we have is how do we find what we're interested in that huge set of data? And so having an appropriate finding aid, which has information like title, author, publisher, and so on, but also has keywords and maybe in this case, some more specific identifiers that relate to the content of the file, that's a really useful thing to have. So each individual JSON-LD document is a discrete data set. So the idea is the data, and then the descriptive metadata goes in the same file. We have different sections set up. Now, things like SciData, like methodology, like system, like data set, and so on, those are things that are specifically defined in the SciData ontology, so that when we convert this structure into its equivalent triples, then there is something in that set of triples that specifically talks to the sources of where this information came from, or where the methodology data resides. So the ontology is, again, kind of creating a schema or a structure of how the information is represented in the graph, helping us to be able to write SPARQL queries against the data. I think JSON-LD is like the ultimate data format simply because it's a text file. It can be stringified, which means you can take out all the extra spaces and make it just one long string. So you can compact it in that way. You can store it in a database table if you really want to, if we do some of that. It's a great format for representing data in a general sense. Now, what we have that is a really important part about this is the data set section has some defined elements in it, and you can see here data points, which are individual, like physical property data series, which are groups of data points that have some logical connection to each other. They were done over a range of temperatures or something like that. And then, sorry, that's data groups, and then data series, sorry, are for spectral information, where the fact that it's a lot of data, you know, all with incremental, equal increment values on the x-axis, for instance. So those are defined. You then put your data into these sections to capture it. For methodology and system, though, we've created these aspects and facets sections. And there's nothing special about those words. The simple premise of how I came up with those words is they had to be different from one another, so I could specifically reference to them, okay? So what that just means is, in the context of putting data in here, anything can go in the facet section, anything can go in the aspect section, because those are specific to the particular data that you're working with. The SciData ontology can, one, not represent those, because it doesn't know anything about what those are going to be for any individual data set. If this is used in chemistry, we might imagine in the system there's going to be some chemical information, but if this were used in biology and they wouldn't be using chemicals, they might want to use an organism, or they might want to use a target or something else. So we had to leave these open. And the key thing about those two being open means you also need to semantically define what the meaning is of the data elements you put in these sections. And so that's where the context file comes in, and we'll talk about that. Here's just a little bit more about the kinds of things you can put in the data set section. We've evolved this a little bit over time, as you might imagine, because again, data structures need to be kind of understandable in terms of what they can and cannot do. But for instance, data group can have data groups underneath it. My common usage of data group is just to have data points underneath it. And the key thing is in here under data group, the data point section actually just points to the data points that are defined in this document. So this is an internal reference. We could also make it an external reference if we wanted to, but the whole area of trying to link JSON-LD documents together is one that we really haven't gone down the path of yet, because it's complicated enough as it is here. Okay, so here's an example JSON-LD document that we created. In the US, NIST, the National Institute of Standards and Technology, has a campus in Boulder, Colorado, and they have the Thermophysical TRC, Thermophysical Research Center, and they have collected over the last almost 20 years, it's about 2.8 million data points on physical property data, ranging from solubility to density to permittivity data and stuff like that. What we did with that was we said, this is a great data set. It's actually represented in XML. It's an IUPAC standard called ThermoML. And what we did was we said, okay, let's understand this data set from its data structure, and then let's understand how we can put it into SciData to be able to represent that data equivalently in SciData, as opposed to the XML that it's in, that the TRC provides. We're just about to release 3 papers on this. One talking about the piece of software we wrote to do the conversion. One talking about a MySQL database version of this that we created, where we showed the model from the TRC in that, or from the SOMO-ML in that, and then a JSON-LD set, which will comprise of about 120,000 JSON-LD files to represent all of this data that's in this data set. This particular example is from one particular file, and so we've got a naming convention and then an ID, a UID that is generated after that naming convention. So we can point to the file where it exists online, but we can also reference back in the sources section back to the TRC data where it's actually published, because it's a formal data publication. And then in this case, we only have one data point in this file. I picked it out because it was the smallest file. So the one data point in this case is a triple point temperature for a crystal. We represent all of the metadata elements here that are necessary to characterize it correctly. And you may look at this and go, well, it's kind of overkill, because you've got not only the numeric value, but you've got decimal places, and you've got sig figs. But in a general sense, we kind of need to represent the data as well as we can from a characteristic sense. from just a practicality of being able to, maybe wanting to use any of these data elements. Okay. And also from the standpoint of, if you know anything about JSON, there's actually a problem with JSON where a numeric value like this can have, maybe normally has a 0 at the end, but when you organize, oh geez, I've lost my feed. Okay, what's going on here? It says okay. Maybe the Wi-Fi has gone, it's not happy with me now for some reason.
You're still. Oh, no, you're right.
That's just the camera, so
Yeah.
I've stopped sharing because, hold on, let's see if I can reshare here. It might be as simple as me just resharing at this point. I'm not. Okay,
Yes.
I'm back. Okay. Apologies about that. Technology always gets in the way. Right? Okay. Yeah. I got it. All right. So, like I said, in JSON, if there's trailing 0, when you reformat JSON files, you can very easily lose the trailing 0. So, of course, that's a good reason why we would also want to make sure we capture the significant figures in here, just to make sure that the data is still represented correctly. Okay, so there's a brief introduction to what SciData is. We have a problem, and the problem is we're going to take this data and we're going to put it in a graph database. The problem is, again, from a versioning perspective, if we want to be able to update the specification, organize the data in the files in a slightly different way to make it easier to search in the graph, we want some way to easily do that. And I already mentioned about adding the @graph in the JSON-LD document so that we have a graph name on our data set. So what we basically said was, okay, we've got to have some kind of software to be able to manage the process of taking our data that we generate in JSON-LD and putting it into the graph database. And that's what we now do with this product we call SciFlow. Basic idea is we need to think about the original data source that we've got the data from. We've got to model that. And then obviously that really means how do we identify what pieces in this goes into the JSON-LD document, into the methodology section, into the system section, in the dataset section, so that we can then create the file and put it into the graph database that we can then start searching on it. There's two pieces to this. One is just trying to manage the workflow to make it easier for us to administrate this stuff. Because at this point, based on all of the work that we've done, it's quite possible we're going to end up maybe, let's say March of next year, with over 1 million JSON-LD documents, and those are all going to be in the graph. And the only technical person that is now on the grant right now is me. Okay, I am it. So if I want to ever get any sleep, I have to make sure I can manage this. And that's not even all that I need to do, but we'll get to that in a second. So management of the workflow is one thing, but the second piece is what I mentioned about the methodology and the system section. The metadata that we put in those two sections is completely whatever it needs to be for the data set that we're converting. If we don't have a semantic annotation of each of those data elements, then we cannot generate RDF that means anything, okay? So the one thing that we also do with the SciFlow software is we use it to generate what we call crosswalks. And crosswalks are taking a metadata element from the original source document, working out where it goes into the SciData JSON-LD structure. And then once we've done that, we also assign to that particular metadata element what the semantic meaning is to it. So we actually link it to an ontology definition. If we do all of that for each of the elements, then we can generate what's called this context file. And the context file, again, is where in a JSON-LD document, you end up creating a file that does the annotation of the metadata elements in the document. Okay, so two practical reasons that we need to do. What we also found was that there was another thing that made sense for us to do, and it was from the MySQL or the relational database perspective. Has anybody heard the acronym DRY? In this context, it means don't repeat yourself. Okay, and the idea in a MySQL setting is, you abstract everything out into individual tables so that you only represent them once uniquely, and then you refer to them in other tables using the foreign key idea. What we wanted to do was do the same thing in the context of the graph, because if I put 5, 10 different data sets in the graph about a particular chemical substance, I don't want to have to rely on whatever metadata elements are representing those different chemical substances, because they're all going to be, or they could all be different, okay, in terms of how we put the data in the graph. So rather than that, what we also do in the SciData workflow is we normalize the data files. And what we mean by that is we look in a database table. So we actually have a separate MySQL table, database with tables in it that is behind the SciFlow software. And what it does is it keeps track of not only the data that we actually put into the graph, but also of the chemical substances that we've put into the graph. What we do is, for every chemical substance, we generate what we are calling a chemical twin JSON-LD document for, which is a generic representation of that chemical substance. And then whenever we put a data file into the graph, rather than just putting it in as is, we identify what the chemical substance is in that file. We see if it's already in the graph. If it is, great, we just link directly to it. Or if it hasn't been created yet, we create that file, we put that in the graph, and then we link the data to that. And in that way, no matter how many data files come in that have data about a specific chemical compound, they all link to the same representation of that chemical compound in the graph. So we have a much better way of organizing our data. I keep forgetting I'm pressing the wrong thing. So this is that process in action really quickly. So this is a file coming in. It has some nominal metadata elements in it. What we do is we look through those metadata elements and try and find a unique identifier that we can use to basically search our database table. So the database table not only has like the generic representation of the compound, but it also has a list of all its identifiers and all its descriptors. We do that by aggregating data from a lot of different external resources like PubChem and others. Once we've then identified from this metadata what the compound is, and either we've found that it's already in the database, in the graph database, or it's not, and we have to create it. Once we've created it, which is shown over here, then we actually just link it together by replacing the metadata element with this particular ID. And in this case, this is an ID where it actually points directly into this file, into this particular section right down here into compound 1. And we've rephrased that now as substance 1 rather than compound 1, because of course substance is more generic, but that's the example I have here. So there's a lot going on here other than just generating these JSON-LD documents. Okay, so that's SciData, that's SciFlow. And then what we've kind of moved on to is thinking about, well, okay, this seems to work as an idea. What else can we do with it? And one of the things that I was fortunate enough to have was a student take my chemical informatics class who was a computer science major. And once I realized it was a very easy class for her because she was a computer science major. She also happened to be a chem minor, which is really good. And I had put this project proposal into NIST in the US for a prototype project where we would create, and again, the DRN idea is Jeremy's original idea, Digital Research Notebook, where we want to use SciData as the basic data capturing format for data in Digital Research Notebook. So what we built was the student, I basically gave the student free rein to decide how they wanted to do the interface because they were the information science student. So they chose React to do the interface. We used Django and Python in the background, but there is some Node.js in there. MongoDB as the database, because that's a JSON database. And then the other two pieces are to do with blockchain. So Bloxburg, which actually I think has now just been renamed something else, is a academic specific blockchain. The idea was that academic institutions could use that blockchain to be able to try out blockchain-based technologies for free. Solidity is a piece of software that you can use within Python to be able to talk to the blockchain. And so what we have here is a research notebook that nominally the front end will allow you to put data in. It gets saved in JSON-LD documents, and then those JSON-LD documents get stored in the Mongo database. And then we do something really interesting with them. So what I really wanted to do was to have a system where we could, at least nominally, propose that we have a trust in the data that we capture. And the way that we do that is as follows. We're linking the creation of the JSON-LD file to Git, which is a versioning software, right? And then to the blockchain. So the idea is this: we start out with a template JSON-LD document, which we can populate with data. The interface is what we use to populate the data. And after a certain period of time where there's no activity, the file gets saved in MongoDB. We then immediately take that file, convert it to triples, right? So in this case, the template file is converted with its whatever small amount of data is in there into triples, and we store those triples in a text file, okay, with one triple on each line of the text file. Then we put that in a folder that is versioned by Git, and then we generate that data in triples is then actually put onto the blockchain as the first block of a chain relative to the evolution of this specific file. Initially, we were doing hashes, as is kind of typical with blockchain, that you hash some data and you put the hash on the blockchain. But we actually found you can put sort of a decent amount of data actually into the block on the blockchain. And we have some interesting ideas about why we might want to do that, which we'll talk about in a little bit. Okay, so this first version of the file has been created. Then as we add in the interface more data to this particular, whatever it is we're trying to record, that JSON-LD document gets updated. It gets saved again in the MongoDB. We convert the triples. The tripled text file then overwrites the version that was in the folder that's monitored by Git. Git does its thing and just gives us the differences. And then those differences get put onto the blockchain in a transaction. In that way, we capture the initial file, and then we capture all of the changes that happen from an RDF sense in the semantic representation of that data in that file. This can theoretically go on, forever, because as people move around the system, they might be interacting with different files, but they may come back to another file and add more data to it later. So we can nominally version the file out over time. The nice thing about this is we've done preliminary work to see if we can take the data back off of the blocks on the blockchain, reintegrate them together to generate what the RDF was at any particular version. And then we've been able to do that, but one thing we need to do further is convert that back to the JSON-LD file. And in that way, we could potentially kind of regenerate lost data. If we happen to lose the JSON-LD file, we could recreate it from its history on the blockchain. There's some stuff we have to do with framing, which is a JSON-LD concept of how you would put that back together. But I'm pretty confident that's going to work out. The only problem I have is the student has already moved on to a job and is earning probably more money than I make. So that's just the way it is, right? So this was, like I said, this is a prototype project. We were working with data from NIST in their additive manufacturing program. And we're going to finish writing this up at the end of the year, and there will be a paper on this sometime in the first quarter of next year. This is just the overall process. You can see this is the information science student who knows how to do process diagrams. Not something I put together. Very interesting idea. And the takeaways are that we can, come on. There we go. Backwards. Okay. We started with XML files. We did XML to JSON conversion, and we put the files together. We did a little bit of metadata in the interface to be able to set all that up. So this is not, it's not quite as complete a prototype as I had hoped for, that there would be, simulating a researcher, in the lab, typing in data in the interface for lots of the stuff and being able to put it in the graph. But we've basically got all the pieces. It's just a matter of kind of expanding the prototype out. Large data files, as you can imagine, are somewhat of a problem. JSON-LD conversion to RDF when you have big lists in JSON-LD is not good from how the RDF looks. So that we're going to have to optimize that. And like I said, we're trying to work on how can we regenerate the original JSON-LD if it gets lost with the concept of framing. All right, so going back to what I had mentioned about the creation of a unique representation of a chemical substance in the graph, because we needed to have that, that specific dry representation, single representation. That ended up being a very interesting idea. And Jeremy and Simon and Egon and I were on some calls where we talked about this as an idea. I've evolved this a little bit further. And the idea is that a digital twin of a chemical compound or chemical substance is very abstract representation. It's not talking about a physical sample of that material anywhere. It's talking about just the abstract representation of what this compound is and the explicit information that we can write, or in an RDF sense, we call it assertions that we know about that particular molecule. In this case, what we've decided to do is to put in information about identifiers that we know about, and that's IUPAC systematic name, ACS systematic name, but also things like inchies and inchy keys and smile strings and stuff like that. Descriptors about that chemical substance. The descriptors are, general things like number of atoms of a particular element, number of heavy atoms, or something a bit more sophisticated like a Takemoto fingerprint or something like that. And then what's more interesting to me is the idea of having a molecular graph in this representation. And what I mean by that is really just, can we represent in the graph the elements that are in this compound, if this substance, the atoms, and then the bonds. And if we can do that, which again, I'm taking a little bit of liberty here saying we, quote, explicitly know this information, because certainly a computational chemist could argue with me, well, we don't know that bonds are really there. We just infer that they are because of what we see when we do our calculations. I guess I'm taking a little bit of liberty with that, but anyway, this I think is useful because of what we might be able to do with it. We're going to put this information in a JSON-LD document, as I said, and this is kind of what it looks like. I realize that's a little bit busy, but in a general sense, we have, should show you a bit more. There's the finding aid again. So this is descriptive information that would help us find this particular chemical twin file. We have some chemical metadata. We have the general stuff that I talked about, like just formula, molecular weight, that kind of stuff. The identifiers, the descriptors, and then this molecular graph. If we go on to look at this in more detail, here's the identifier section, or an example of what an identifier section might have in it. And the reason why this is important is if we go back to the SciData workflow example, workflow example, we need to be able to have a lot of identifiers in here because we don't know how the data is going to be identified coming in. So we need to have a way to try and match it up. Obviously, in this case, we have some identifiers and some of them we don't have, for like Chembl or Reaxis, for instance. Descriptors can be a number of different things, right? We pull these from PubChem, from Wikidata, from Classifier. Classifier is a website, I forget which the institution is in Canada, but this is basically a chemical ontology that has been used to characterize in different types of chemical substances, about 82 million chemical compounds. And so these chem-ont terms here are the ontology terms for organic compound, at the top, I think it is number 1, and then more specific ones as you go down. So you're kind of representing in an ontological sense the nominal functionality that's in the molecule. A lot of these other descriptors, again, come from PubChem, but in other places. And there's also the possibility we can create more descriptors if we can infer more information about the chemical substance from the representation that we have here. And I'll talk about that in a second. So this is a very simple example, obviously, for demonstration, but the idea here is we represent the elements at the top in a section. So we've got oxygen, because this is molecular oxygen. The chemi reference there is to the oxygen atom in an ontological sense. We have atoms, they reference back to the element. So that's, again, an internal reference. And in this case, they indicate that there's one double bond that's attached to that particular oxygen atom. Obviously, the same is true in the second one because this is O2. And then finally, we separately represent the bonds, and that bond is of order 2, so it's a double bond. And then we can actually assign that it is attached to these 2 particular atoms. And so we have in a sense, a semantic representation of the structure of the molecule. This is very interesting because we can do something with it. If we put it in a ChemTwin file, and okay, try and do that again. Right. And we have a context file. I talked about context files before, and this is going to be a little bit more about that. We generated a ChemTwin ontology to go along and actually define the pieces of the structure that we put in the file. And that's necessary, again, to be able to semantically define it. So here's a part of that context file. This is some of the higher metadata elements that's in the SciData JSON-LD file that we have to specify. But then if we get into the chemical twin, this is the general metadata. And what you can see is we have to give these semantic representations. We have to assign them. They just match up with what the names of the elements are. So that, again, when the file is converted from JSON-LD into the RDF, each of those triples has the right representation of the meaning of the subject, the predicate, and the object. If we go down to the next section, this is where we now have our representation of the descriptors. And again, it gets complicated here a little bit, but there's also the issue that maybe somebody hasn't already ontologically represented these things yet. So then what do you do in that situation? Well, we can play God and just create it ourselves. But maybe that's not the best thing. So maybe you go and talk back to the developers of ChemInf or the other ontologies that are in chemistry, and there actually would be a way to do it and make it more appropriate. So here's actually I have those two the wrong way around. So the previous diagram is the descriptors. These ones are the identifiers, even though of course that's not correct in this sequence here. So identifiers there. And then we have to represent the structure of that molecular graph. So we have representation of the atoms, the bonds, the charge if we need it, and so on. Okay, so what does this mean? Well, what we can do is we can create these files, we can put them in a graph database, and we can do searches on them. So this is a specific search for the INCHI key that's associated with each of these files. Very simple example, because it's nice to show a simple example, otherwise it can get too complicated. So this is the Wikidata property for INCHI key specifically. And then what we want to do with this is actually something that I talked about at a meeting in 2017, where I was like, you know what, we should be able to do a semantic representation of molecular structure. And what I basically went through an example of was, can we reason using OWL, which is the web ontology language, that an atom in a molecule, for instance, is chiral. I think I look at that as kind of like an exemplary use case. If you can have enough intelligence to infer that kind of thing for a particular carbon atom, then it would be really amazing. And what we did was, so we represented, bonded to minimum of four atoms, and it's not moving on. So we can infer, anything yellow is inferred here, so we can infer that a particular atom is a chain atom, which means it's bonded to two more other atoms. And then we have instances down here, so we can see each of the individual atoms that are identified to be represented like that. what we did was we looked at can we try and infer that the particular central atom of the structure, which is this one's ethane, but the one we were trying to do was bromochlorofluoroethane. And in the end, for some reason, the diagram is not showing up as I had got it, but I was able to get it to crudely infer the chiral center. But I mean, it looked okay at that point, but I have played with this a lot since then. And it really, using OWL to try and model this, has not really worked very well. So I bring that up because what I want to use now is called Shackle. And Shackle is a newer specification that the W3C has put out about RDF. And the idea is that Shackle is nominally a validation tool. So the idea is that you write what's called a node shape, this whole thing here, to validate a particular structure of triples that you have in your triple store. So for instance, this node shape is trying to represent a single bond. The way we do that, again, this is based off of CTO, which is the chem-twin ontology. We identify that the target class, meaning the starting point, the node that we start in terms of defining this, is a bond representation, or an atom representation. And then what we say is, okay, a single bond has to be starting with a bond class, and the property of that bond is that it has a bond order that is only one, right? That it's a single bond. And then we also add a property that says that that bond also has a maximum and a minimum of 2 atoms. So we actually have a representation of a single bond with 2 atoms, one on either end. And I know that seems very simplistic, but that's what you have to do in a sense of triples, because triples are very minute, right, specific representations of pieces of information. They're not telling you too much. And so the key thing about this is a very nice idea for being able to validate the data that we've put into our chem-twin file. But it turns out that Shackle has some advanced features, and one of the other features is you can use it to infer information as well. So this is really going to be very useful because one, it can validate the data that we've put in the graph, but then 2, it can infer on top of that data other information, and then that information also gets added to the graph. So just to give you a quick example of how that would nominally look, if I get out of here a second, hopefully. No, I don't want to create Acrobat PDF. Thank you. Cancel. I use this software called PyCharm. PyCharm is an IDE from JetBrains. And I have the same example here for the single bond. But what I want to do, and I can't show you it in full, and I'll explain why in a second. What I want to do is get something like this, where I can represent and infer a carbonyl bond. So we know what a carbonyl bond is, carbon double bonded to an oxygen. What we would want to have is that the target class is a double bond. We want to say that one property has bonded atom is a carbon atom. The other property has bonded atom is an oxygen atom. So we actually have the representation of the carbonyl group, as it were. And then if we could use this in our structure to not just validate that everything is set up correctly to represent that, but then also to infer that it's present in the molecule, then that's a really useful thing, because we could build that out to do a whole bunch of functional groups. And literally the shapes file that we're talking about here could be applied to all of the chemical twin graphs that are in the graph database. So we could infer carboxylic acid groups that are present. If they are present, we could infer carbonyl groups, amines, and any other functional groups you can imagine with this kind of setup. The problem that I have right now is the technology. And I'll just quickly mention this. I'm using a plugin for this particular demonstration, and for some reason, it is not correctly reading the ontology files that I have, or file that I have. And it reads some of the definitions of the ontology terms correctly, but some of them it says are not present, even though I know they're present in the file. So I cannot actually run this without errors and show that this actually works. And I'm very frustrated about this. It's about a month I've been working on trying to get this to work. Anyway, enough said. Basically, I believe that this is going to, eventually I'm going to be able to fix this, and we will be able to infer chemical information, obviously that is really useful from a chemistry perspective, on top of this very interesting representation of a molecule in a semantic sense. And so that's something I'm very optimistic we will see very soon. So let me just finish this up. I know I've rambled on for quite a long time here. So I will make sure to share these slides with Jeremy. There's a whole bunch of links here to lots of different stuff I've been talking about. I believe that semantic representation of data is going to be the way we do this in the future. Exactly how it's going to evolve is a really good question, because I think we're really right at the start of it, but there's a lot of opportunity in this space. And I thank you for your attention. And if you have any questions, shout them out and I will try and repeat them for anybody that's online. And there may not be anybody online, because I think